Hello and welcome to our team's VoiceThread presentation. Our team is designing custom RFIC and 3D printed antenna designs for FMC weather radar application operating at 36.9 GHz. Our team members are Sabir Ahmed, Jean-Luc Cassignol, Benjamin Coons, Alex Schaff, and Joe Nestor. Our project advisors, Professor Ashvin S. Daryush, and our graduate student advisors are Nicholas Bromhead, Kevin Singh, and Joseph Fassbinder.
Our project aims to tackle the issues of flash flooding and other natural disasters by designing a V-band weather radar system in order to accurately detect abnormal weather patterns. Flash flooding and other natural disasters cause catastrophic damage to human lives and property. Additionally, global warming has caused a significant increase in severe weather, making the need for accurate weather detection that much greater. High-precision X-band weather radar components are available, but are large and expensive to manufacture and operate. Most current market weather radar tracking systems are based in the X-band frequency range, or the frequencies of 8 to 12 GHz. Most systems tend to use mechanically scanned reflector antennas, which are susceptible to extreme weather conditions. Current systems are not suitable for difficult terrain such as mountains or wide rural areas because of their size, power needs, and range. To the bottom right, we have comparisons of some of the latest weather radar systems on the market. As you can see, these systems tend to be quite power hungry while often being large or immobile. Here listed are the major design concepts of our project, some of which will be elaborated on further in the presentation. For more information on these concepts, please see the appendix section at the end of the presentation. Our first concept is the phased array frequency modulated continuous wave radar at 36.9 GHz. With greater velocity and range accuracy resolution than systems operating at X-band frequencies. Next, our 3D printed array reduces the weight as well as the cost over reflector antennas. Then, we have 4 quadrant panels which are tilted about 15 degrees to track fast-moving rain clouds. Our system has fast beam scanning using electronic phase shifters, as well as frequency coherency, using frequency locking and phase shifting to boost power and steer the phase array beam. Finally, we have low-cost RFIC realization using Tower Jazz foundry process. Some design considerations for our project are that we remain in the FCC allocated frequency bands during the operation of our radar, as well as the environmental concerns in manufacturing our RFIC designs. The FCC is allocating bandwidth for X-band as well as millimeter wave radar systems for meteorological research, meaning that our radar can operate at V-band frequencies without concern. Additionally, to ensure that the manufacturing of our project is environmentally friendly, Tower Jazz, the foundry that we're using, ensures the following: that their processes are free of lead and other potentially toxic compounds required through RoHS and REACH compliance. Additionally, cobalt and other minerals are responsibly sourced and RMI reported. For more information, please see the reference below.
The resources required during this project include the Tower Jazz design kit for electrical and modeling specifications, as well as proprietary SPICE models and substrate information, Keysight ADS for RFIC simulations and microstrip modeling, as well as 3D designs and method of moment EM simulations. ANSYS ASFSS was used for antenna 3D design modeling and microstrip evaluation, as well as finite element EM simulations.
To be clear, we are focusing on the RFIC and antenna component design. These specifications were based off of what would be needed to realize a full weather radar system. So, looking at the RFIC components, the output of the last stage of the VCOs, which would be the 36.9 GHz oscillators, need to be at least 3 dBm. The frequency drift must be less than 100 parts per million per degree Celsius. The phase noise of the free-running oscillators must be less than -40 dBc per Hertz, and less than -100 dBc per Hertz when injection locked. Both of those phase noise values are at 10 kHz offset from carrier. For the antenna, the gain of the array must be greater than 7 dB with a return loss of greater than 10 dB, and a fractional bandwidth of at least 0.5%. We need a symmetric radiation pattern with an axial ratio of at least 15 dB.
Our team's design approach is to have two smaller groups consisting of an antenna team and an RFIC design team. The antenna team, consisting of Sabir, Ahmed, and Joe Nestor, will focus on the design of a 5.4 GHz slot radiator to be upscaled to 36.9 GHz. The RFIC team, consisting of Jean-Luc Cassignol, Benjamin Koons, and Alex Schaff, will focus on the design of filters and amplifiers for VCO and self-oscillating mixer realizations. All designs must be optimized for low cost, power consumption, spatial requirements, and phase noise to be viable for remote weather sensing. RFIC filters are required to have low board space, high quality factors, low associated losses, and 10 to 20 MHz tuning bandwidths. Tuning is achieved with a single-ended HBT over a traditional varactor diode because of improved simulated Q factors as well as linear tuning characteristics found in Appendix Slide 31. Filters at 9.225 GHz use lump designs to reduce chip space required. Filters at 18.45 and 36.9 GHz utilize distributed filters because of decreased size as well as improved performance associated with higher frequency transmission lines. Custom stackups were used to further evaluate transmission line performance, seen in Appendix Slide 32. The lumped RFIC filters utilize a first-order 3 dB design because high filter selectivity is not necessary, and a higher-order filter would require further component space. Initial designs found in Appendix Slide 33 replaced tunable capacitors with HBT and biasing networks. Lumped elements from Tower Jazz results were worse due to parasitics associated with component geometry. Insertion loss of the bandpass filter at 9.225 GHz is negative 2.27 dB, and input return of the bandstop filter is negative 1.5 dB, meeting the Barkhausen criterion. The distributed RFIC filter designs utilize idler filter designs to reduce board space required. HBTs are biased from 0.45 volts to achieve near linear tuning as seen in the graph below, and in our results in Appendix Slide 31. Tuning is done at the end of the stub with DC biasing networks as well as DC blocks to isolate bias voltage. The filters have poor selectivity but improve spatial requirements with about 1 mm squared board required for every filter design. Metal layer 1 was used to improve attenuation over various other metal layers such as metal layer 4 and metal layer 5, while metal layer 6 was used as the signal carrier. Both at 18.45 and 36.9 GHz, the losses associated with the filters meet the Barkhausen criterion for oscillation.
For the VCOs to work, the amplifiers and filters must meet the Barkhausen criterion. A more in-depth explanation of this is given in Slide 27 of the appendix. What this means is that the insertion phase of each amplifier needs to be around 180 degrees, and the gain of the amplifiers need to be greater than the insertion loss of the filters. The gain and phase are difficult to meet at the higher frequencies, especially 36.9 GHz, due to the Miller effect, which reduces insertion phase and gain due to parasitic capacitances within the HBT. If the amplifier does not meet the phase requirement, then the phase can be improved by meandering transmission lines. However, this uses more chip space and increases losses. Also, the amplifier by itself needs to be stable. This is because the instability of the amplifier by itself would create unwanted oscillations. Due to space requirements, options are limited for improving gain and stability because there is no room for matching networks. The parameters used to measure the gain, phase, and stability are the S21 and mu parameters. Because of the high operating frequency, the amplifiers must be cascaded. This means following a common emitter amplifier with a common base. The cascaded amplifier has similar characteristics to a common emitter amplifier, but with less parasitic capacitance effects like that of a common base amplifier. The amplifiers must also be distributed. This means adding transistors in parallel to each other. This doubles the number of transistors and halves the output resistance, but it also doubles the gain. This is more effective at improving gain by cascading when gain is less than or close to 1. The amplifiers also need to be active biased to remove any temperature dependence, which is important when climate control of the components is impractical, as it is in the case of a mobile weather radar. The detailed schematics of the amplifiers can be found in slide 36 of the appendix. In the table shown are the results of the ADS simulations. The graph to the right shows the sample results for a frequency sweep of the amplifier at 36.9 GHz. The figure in the upper right shows the block diagram of the oscillators. The results of the open loop simulation are shown in the top table. For an effective oscillator, the gain needs to be greater than 1, which all of them are. The phase should ideally be 180 degrees, but the phase of the open loop oscillators is poor, especially at 36.9 GHz. This can be improved with meandering transmission lines, and this was done in the closed loop simulations. Results of the harmonic balance of the closed loop oscillators are shown in the bottom table. The only VCO meeting the 3 dBm requirement currently is the 18.45 GHz oscillator, whose full harmonic balance results are shown in the chart to the right.
Okay, for my portion of the project, I'm working to characterize the ABS substrate. Currently, there is no existing data for the complex permittivity of ABS plastic above 10 gigahertz. So our plan is to design 2 microstrip lines, one for 9 to 22 gigahertz and the other for 20 to 40 gigahertz. We're going to build models in ADS and also in HFSS 3D models. And we're going to take the simulated data from those 2 models. And once we get them to where we want them, where they look good and match up, then we're going to fabricate them in the lab and then do in-lab measurements. And then we're going to take the data from both the simulated and the in-lab measurements and compare them. And we're going to be able to extract information that's going to give us insights into the complex permittivity. Okay, so to take a quick look at our HFSS 3D model, if you take a look at the table, we have the dimensions for the microstrip line, both width and the length, for both the 22 and 40 gigahertz designs. We were able to fine-tune these dimensions using the ADS line calc tool, and taking the dimensions, we were able to construct a 3D model in HFSS. If you look at the right, the model that we have on the right, we have the microstrip line in yellow in the center there, with the substrate being in green, and then there are the SMA connectors at both ends. And then this is all enclosed within a PLA plastic enclosure. Currently, our simulation results in HFSS do not match up with our ADS results. We're seeing return losses that seem to be too high. If you look in the appendix, I think it's the last slide, you can see that it doesn't match up. So we're trying to tweak the model and get it to agree. It may be an issue with the width of the substrate or the thickness of the microstrip line. We're trying to rectify that. But once we get it to agree with the ADS simulations and we get the model approved, then we're going to move to fabrication of the 2 designs. And once we fabricate them, then we're going to be able to do our in-lab measurements.
Along with the design shown in the previous slides, we will be using a prototype of a phased array as a 2x2 array of slot radiators in the weather radar system. This design will be based on a research article which showcases how 3D printing can be used to manufacture antennas which was done by Shaker Al-Kharaki. One of the benefits of using 3D printing is to negate ohmic losses due to metallizations, but when using a material not metal, in our case ABS, the losses can be negated. Slot radiators can be used for arrays because of the sidewall corrugations that can be used to steer the beams. However, in our current iteration, since we are doing single element, no sidewalls are printed in order to save material. In our current iteration, we are scaling to lower frequency of 5.4 gigahertz and with the consideration of using ABS in order to evaluate the methodology to apply our testing to the array at higher frequencies. Next, we chose an aperture coupled feed to create a wider bandwidth of the antenna. Our dimensions are shown here. While we have a design for this lower frequency prototype, there are issues with getting useful simulation results due to design issues. As in this picture here, where we are struggling to achieve more than 10 dB of return loss, and it is not resonating at the proper frequency. Our model for the antenna is here. As you can see, it is a dielectric resonator antenna with a rectangular slot opening in the upper part of the dielectric enclosed cavity. The SMA connector jack feeds a signal into the microstrip feed line for the cavity antenna. This operates as a metallic standard enclosure with a open-ended microstrip line terminated at the center of a rectangular slot in the microstrip ground plane. The jack has grounding in the outer shield affecting the ground planes and the side of the dielectric antenna. So a signal is fed and goes through the feed line, and the dielectric antenna is excited by the slot cavity aperture with TE010 mode, and radiation comes out. And here are our cross sections of the design. So you can also see the aperture coupled feed with the ground plane below the substrate and a ground plane above, and our feed line below, coupling out into the antenna. In our weather radar senior design, we encountered some obstacles in our design process. With the RFIC design, there were issues with using the TowerJazz PDK for inductance calculations. And the test boards will not be manufactured due to the long processing time of multi-project wafer. In addition, the lumped elements were required in all designs, including distributed designs to isolate DC. Lastly, the 3D modeling with the antenna posed to have issues due to the changes in the design choice and process, as well as with the consideration of the manufacturing with the 3D printer on campus, which also has restricted access.
So the future work that we have moving forward for the RFIC team, closed loop BCO analysis, SOM design, final design layouts, method of moment, EM simulations, EM optimization of designs, final design tape outs. And for the antenna team, we have refining the HFSS microstrip models, fabricating microstrip lines for the ABS characterization, and 3D printing the scaled 5.4 gigahertz antenna. Once we have the 5.4 gigahertz antenna, then we plan to scale up in frequency and down in dimension, and eventually towards our goal of a 36.9 gigahertz antenna and a finalized antenna model. So this is our updated budget. If you look at the main table here, this is the budget with the RFIC test board components. Unfortunately, with time constraints being what they are, we will not be able to construct the test board. So if you look below, you have the budget without the RFIC test board components, obviously being much smaller. It's just the SMA and the SMK connectors for the microstrip designs that we have that we're going to fabricate to characterize ABS. And if you look to the right, we have the conceptual block diagram of a voltage controlled oscillator test board design using the requested funding, and then below that is the conceptual block diagram of a cascaded oscillator based transmitter and a self-oscillating mixer test board using the requested funding, which unfortunately, like I said, we won't be able to design, time constraints being what they are.